We had actually called this part the pants when you're actually looking.
Hey everybody, it's Norm here from Testin. I got a really special treat for you today. Not only do we have this Formlabs 4L 3D printer that we've been using and loving, we also have teams that worked on the 4L here to help us with a teardown and disassembly. So I want to welcome to our studio Seth and Larry. Seth and Larry,
Thank you.
welcome.
Yeah, pleasure to be here.
Yeah. So tell me about your roles on this project, a project of this size, a printer like this, and what it takes to get something like this to market.
Yeah, sure. So my name is Seth. I lead our hardware systems engineering team, and I led the 4L program sort of through the last year of development with a focus on print success.
Yeah, my name's Larry. I lead our mechanical engineering team developing SLA products. I started off basically being the mechanical engineering lead of the program from concept all the way to the point that it shipped. So in many ways, this is my baby, and we're getting it out into the world.
And my hope for this video and for you guys out there is we're going to be tearing this down. You guys are going to be hopefully completely open about the design decisions, the components, what makes this work, what it took to design a printer of this size compared to the Form 4 and even the past printers that you guys have made. Every product is a culmination of thousands and thousands of conversations and debates and decisions. And so I'm excited to tear this down and hopefully put it back together by the end of it. You know, while we have this open before we start taking things apart, do you guys look at this and think of it as like systems on top of each other? They're kind of discrete, solvable problems that you have different teams in the product development stage, like working in tandem, solving. Is that how this product comes together?
So it may not look like it, but we sort of think about this as a obviously tightly integrated product, but within this there's the LCD module, which we'll take out and talk about. It's called the LPU. We sort of describe things internally differently, and then we call them something externally. So I'm going to screw it up a few times. And the backlight unit as well. So we'll take those out. But from the get-go, Larry alluded to this as well, but we try to design things that will not break and will last a very long time, but we knew that those would be sort of two key components that were the, both core to the print process, but also, more likely to be serviced. So those are both really easy to take out and replace. And as such, they're part of the whole system. We also treated them like their own products.
What are the factors, or maybe it's a single factor, that determine the size of this machine, right? Like is that one of the first things that you start with?
Yeah,
that's a good question.
That's a good question. I mean, I think we started off looking at a couple of different things. I think like build volume is the thing that we usually size our printers around. That's like undisputable, can't shrink smaller than the build volume. And and a lot of that came down to kind of what LCD size were we going to do. And no, that defines our XY. And then for Z, for example, like what we can probably make the printer as tall as it can be. And we actually used a lot of our F3L data to look at now what are people printing on F3L and looking at kind of our distribution. And we came to around a 350 millimeter tall build height, which is, I think, plenty large for this size and that aspect ratio.
There you go. All right, let's take a look at the side here. So let's take a closer look at this part. This was off of that right side panel, and this is where the cartridges live, right?
Yep.
Tell me about this design, because it seemed like a lot of connectors to come out of just a thing that the resin cartridge sits on.
Yeah, so actually these, if you kind of look closely, for people who've actually looked at the Form 4 assemblies, this is actually the exact same dispense assembly from Form 4. So we're sharing across both product lines. There's a motor here basically that drives a actuator that helps us dispense on our cartridge. So basically it's a finger that pushes into our bite valve. And then we have a load cell here to be able to actually read out the weight left in the cartridge to see if we're running out, if we're actually dispensing properly. So if we're trying to dispense but we see no changes in the weight, our cap on top might not be open. So yeah.
Tell me about the load sensor then. Is it just literally the weight? You guys have in your a chart of how much this thing should weigh with the container, and
yeah. So I think obviously it's for the weight, but we actually end up doing calibration at the factory where we used a known set amount of weights to be able to actually build up a load cell gain and offset curve. And then we use that throughout the printing process throughout lifetime until hopefully it doesn't break, but to monitor for different instances. If you're running out of resin, for example, that's when we throw a cue on the UI to say you should probably put in a new cartridge. And we do some smart things about how we do dispense, and like we preferentially empty one cartridge out first, so you could have access to kind of one cartridge, refill that, instead of kind of having both cartridges almost run at the same time.
Is that a new thing?
This is actually, I think it's shipping like this week.
Okay, it was like, absolutely, because you guys have the same cartridges as the 4, and I noticed that when we were reviewing it, it went dispensed at the same time. I'm like, oh wait, I want one and then the other.
I'm really glad you. I'm really glad you said this, because we recently shipped this. I've been pushing for it. The trade-off is that, and the reason it was like this originally on Form 3L, is that when you dispense both at the same time, you double your dispense rate.
Yeah.
So that obviously has some benefits, but with the faster dispense rate on 4L, we can basically get away with dispensing from 1 without ever causing the dispense rate to limit the print speed. That's generally the goal, right? It's like, for everything that would limit the print speed, you make that no longer the limiter, and then it's something else. So we obviously never want the dispense rate to limit print speed, because it's one of the easier knobs to turn. But yeah, I think like as of the latest firmware update, we'll now dispense entirely from 1, and then go to the other.
Did it ever get to a case where if someone's printing something with a large surface area, it was printing faster than a single cartridge could dispense?
Yes, and what I will, one thing I'll is that the change in logic will not break in that scenario. And so the way that we do is we measure the amount of resin in the tank periodically, and if the dispense of one cartridge is not keeping up with the rate of consumption, it'll dispense from both. So it prioritizes doing just one because that's more convenient, but in sort of extreme edge cases when you're printing very large, very dense parts in some of the faster resins, we'll dispense from both.
Yeah, and so you have this flow chart of possibilities as the print's happening with all these variables, and that also informs how often you are gauging the load, engaging the
and we have
tank.
that feedback mechanism. So we actually have a level sensor for our resin to know when we're running low on resin, to tell the dispense system to dispense, and then it goes to having the load cell actually look at the load of the resin decreasing to see that we're actually dispensing. So we were using our sensors kind of in a loop system to be able to actually just know that our system is functioning properly, or throw an error if there is an issue or something that it's sensing.
All right. How you guys are happy with the accuracy of this? I mean, I know in the past, I myself have put weights on top of a cartridge to fool the system. I know there's resin in there, and the system sometimes doesn't think there's enough resin in there.
I'm pretty happy. Have you ever had to do it with this one?
Not on this one. It was definitely on the 3. Yeah.
One thing we actually didn't talk about yet is these boards that are sort of floating here. So these are both RFID readers. And so every cartridge has an RFID sticker on it, a tag that encodes both what the resin is, but also batch number and things like that, because we manufacture all these resins and we want to track batch to batch variation. But another way that these sort of parts of the system work together is that the resins have different viscosities. And so the load cell, or the system that reads the load cell, needs to know what the resin is, because if we're using a more dense resin, the readings are different. So we tune all of those to the specific resins.
All right, let's get back to assembly.
All right, cool.
Yeah, so all of our screws are actually, we have 2 different types. We have a pre-applied nylock patch, so it's basically nylon in patch form applied to provide the vibra resistance as an alternative to Loctite. We actually also have another type that you see some of our other fasteners that were taken apart. It's a chemical patch that is basically a dry version of Loctite. So it has microbeads, so as you're tensioning the bolt, it creates a chemical reaction that locks it in place. And all of this is to make sure we never forget any Loctite on components. I think we spec it on drawings all the time to say please put this glue on this thing. And there's a lot of faith in everybody assembling, but people are gonna forget things, and a lot of our screws are very critical. So this is our pretty accessible filter replacement. So we actually have a pre-filter that we took off here. That's this catch any large cat hairs and anything. And we have a slightly finer filter behind our shell. And this is all to keep our optic stack clean. This side, as you kind of pointed out, is the intake. And we have 2 large blower fans that's basically pulling air in across the LCD. So this is all basically doing LCD cooling. So kind of the cooling schematic, we pull air in, this is our intake, we blast it across the LCD to keep the LCD cool, and then we vent out the other side of the machine, out the back of the machine. So you'll feel a little breeze coming out the back left of the machine when you have it running. We have our LCD and our kind of optical system, like our BLU, completely decoupled in terms of cooling systems. When we take a look at the backlight unit itself, it's basically within the unit. So this is purely for the LCD.
On the order of 90% of the light that hits the LCD does not actually pass through it and is absorbed as heat in the LCD.
Really?
In conjunction with the fact that we're heating the resin, which is very, very close to the LCD, and the curing process itself is exothermic. So all of these things are contributing heat to the LCD, and this is, LCDs are not typically meant to operate in very hot environments, so we have to pretty actively cool it.
Is that the thing that causes the LCD to be consumable the most, is just heat over time?
In this system, no. We basically set our cooling requirement such that it is not the thing that is killing the LCD. We find that the primary driver of like long-term wear is total fluence, so like the amount of light that passes through the LCD. And that's not strictly a number of layers because every single material has a different setting, different layer numbers. So you could basically think about it as like counting the number of photons that are passing through the screen. And so we have a rig, like Larry was saying, where we have a ton of these screens. We have temperature-controlled liquid baths on top of them to simulate resin, and then we're exposing them underneath with the
blasting it with, and you're doing this in the order of how many exposures?
So what's the fluence number? We have a fluence number which is 30 kilojoules per centimeter squared. So that's total energy passing through any given area on the screen. In practice, with these test setups, that amounts to like a couple months of running, but for like a typical customer, that would be a number of years. And it's like, how many layers? It's like
so I think it's like 5. So yeah, I think our
layers,
like overall machine design was designed around 5 million layers, and that number, obviously a hard number to kind of pull out, but it kind of came from like obviously Form 4 had a layer count, and we looked at if someone was printing the worst case in terms of lifetime, the shorter sprints, and for us that was actually our dental customers. Yeah. So for dental customers printing a full bed of arches, and they're doing that on repeat nonstop over and over, how many prints can they get out of it? I think we had decided from 22,000 prints, which equated to, for that print, it was around 5 million layers.
This printer is at a point of the assembly where there are some components and sub-assemblies that we may not want to take directly off of this printer because of the factory calibration that's needed to get it reworking in, which we definitely want to aspire to do at the end of this. But you guys have brought some components that we can look at. And before we get to those, I do want to maybe put put one of the vats in here and one of the trays in here to talk about how that gets lashed in and this assembly.
Definitely. I think we started development on Form 4 thinking about like what is the ideal tank insertion experience, and we were very set on we want to have a sliding insertion, mostly because it's a large tank and there's a lot of resin, and also when you kind of asked earlier about what's driving machine size for a door style printer like this, to be able to do a similar style of tank drop-in, you need to make space for hand clearance. So if I had to design this basically for a top-down, a screw mechanism, this printer would have to get wider. It's another design consideration, and we said it's going to be really nice if we're able to put this tank in, right, and be able to slide it all the way in, and then latch up here.
All right, let's talk about this, because this is something that's unique to you guys. I've used a bunch of other types of resin printers where once a tank goes in, once a vat goes in, I am screwing a bunch of screws to lock it in. And the goal is to have the film, the transparent film, as close to the LCD as possible, or evenly distributed against the LCD as possible. You guys have a simple latch. The Form 4 has a latch, 4L has a latch. Tell me about the latch design.
Yeah, so I think like one kind of interesting that you will see very obviously here is that there are 4 heavily loaded springs down in here. So the question is like, why is this spring loaded? We actually started off very early in prototype where there was just a assembly that wasn't spring loaded that would basically latch down. I think depending on the tolerance stack up of where the tank ends up, where the LCD ends up, there's just a lot of variability in kind of the positioning. So we ended up basically putting in the springs in here to have a compliant mechanism to be able to always preload the tank down at a known force. What we're actually doing here is actually pushing hard down against the LCD module. So on the inside here, you can actually see our tank has 4 kind of landing feet here. So there's 1, 2, 3, 4, and we're making sure that we're bottoming out on all 4 corners of the LCD during insertion.
Yeah, I think another challenging constraint here, and this may not be intuitive if you've like watched a video of this printing process, but the forces as you are moving the Z stage up and separating the film from the texture, which we'll probably get to later, and then the part from the film are really quite high. And at their extremes, it needs to be able to peel at the maximum force without lifting the tank off, right? Because then your film plane changes, things move around, and you'll end up seeing that in the part. Even if your tank goes back, like the subtlest of differences between layers will end up imaging onto the part, which is bad.
And we iterated a couple times on getting the right spring force and getting the right geometry. So if you kind of look at this profile, we did a lot of 2D sketches of what is the ideal insertion path. I think one of the challenges with this is that you have to basically clear the LCD on the way in, but you have to drop into position at the end, right? I think there's a lot of potential interference paths, so we basically are sliding in until a back hard stop. So in this position here, basically you're actually bottomed out against the back end of this tank insertion rail, and the front latch, we've designed it just to basically pull down and also slightly push back towards the end.
Okay, guys, so one of the questions I've always had is, why do you guys design a tank to be something that you basically, it's consumable, right? And I think what I'd love to do is take a closer look at the components that make up a tank, as well as what's in the 4 and the 4L, a mechanical wiper that you guys have.
Yeah, sure.
Yeah, can we take this and take a look into the camera? Yeah. Okay, guys, this is your tank for the 4L. You guys have made lots of tanks over the years, lots of different, I guess, design philosophies for the tank. The most important thing, as I understand, is this film, right?
There's a lot of important things in there.
One of the important things is this film in terms of the curing of the resin.
Yeah.
Tell me about the different components. When you look at this, what are the things that are important to you?
Yeah, so maybe at a high level, we joke a lot internally that the tank is actually one of the hardest things. You look at it, it sort of looks simple. There's not a lot of parts, but getting this right is really the difference between a reliable printer and an unreliable printer. There's a bunch of different aspects that sort of contribute to that. So starting with the frame, this needs to be both chemically compatible, but also very stiff and not creep over time. The film itself is tensioned, and the exact tension of that film is super important to the print process. If it's tighter or looser, the behavior of the peel every layer will be different. So the frame contributes to maintaining a uniform tension on a per tank basis, but also across tanks.
And tension here, I think, is something throughout product development, we are hunting for the perfect tension.
Right.
Do we want higher tension? Do we want lower tension? Do we want a consistent tension? Because a lot of our material tunings is around a specific tension film. And this all kind of came back to mechanical design. How are we holding that tension? And are we losing that over time, or is it a consistent point over millions of cycles?
Can you explain to the viewers what the difference between higher tension and lower tension as it relates to successful print? And
yeah, it's a hard question. It's not there's not a single straightforward, clear answer, but the way to sort of visualize this is that as you're printing, you start to lift your part up off of the film.
Yep.
And if imagine this wasn't a film, imagine this was like a perfectly rigid surface. It would be like trying to take a piece of tape and peel it off something by pulling on the center, right? That doesn't work. You can't do that. And so what happens here is that you pull up and the film is actually lifting up above the LPU, which causes sort of an angle between the film and the part, and then it begins to peel away. And so there's different forces involved in both of those, but in that first step that I was describing, if this were super tightly tensioned, you wouldn't be able to tent it up. And we can sort of maybe poke at the bottom, right? You can see, a little hard to see in the camera, you can see that it stretches up.
Just a little bit.
Yeah.
A little bit. And that up is against the LPU, that texture. Right.
Exactly.
Okay.
And we'll, maybe when we take the LPU, we can talk about it. But getting that performance really repeatable across printers is important. The number of supports that you have, and we're jumping from tank to supports, which will make sense in a second, is a function of the force that you're applying to the part. And obviously you want as few supports as possible because they contribute to marks on the print, they use material, but you want enough that your part won't rip off of them. And so there's a fine balance here between the tension of the tank, the force that it applies when you're peeling it off of the or lifting it, I should say, off of the LPU, and then the number of supports that you need that's different for every single material to like balance all of those things. And so if you had a tank, two identical tanks, one that was slightly less tension, one that was slightly more tension, you'd see, probably higher peel forces to some extent on the more tensioned tank. The flip side is that like if you under tension your tank over time, if you lose tension and you don't have a perfectly flat surface, you could see artifacts of that on your part. So we try to stay within a pretty tight band. We actually measure the tension of every single tank that we ship.
High tension, but with enough repeatability that you can be consistent across the entire surface area.
Yeah, lifetime.
Okay, so walk me through the anatomy of this thing. Okay, you got the film. I see that it's mounted in. You have a brace here for your calibrated tension. It's all these points. So someone at a factory, is this a machine that basically screws all this in?
Yeah, so so it's kind of start off with, I think originally, you have a film that is not tensioned. We put this into a larger tension ring. So this is kind of a factory jig that we have that basically holds the tension on the large film, and then we basically secure this into, it's kind of a sandwich if you think about it. We have the stamp sheet metal part that both controls the stiffness of resisting the film trying to pull in this direction, and also controls the height of our film draw. Right. So basically assembled between that, the film is already pre-tensioned, and it gets clamped in with these fasteners into the actual tank frame, which is an injection molded part. So kind of the sandwich of both of these components with the tension set points, how we basically get our final expected tension.
And this is designed so the film resting on a surface is never touching that surface either.
Yeah. This is actually a thing that we changed sort of later in development that I really, it was like actually a function of me printing on the printer, and I put this tank down. So like, these feet, like you said, keep the film off the surface. But if you're on a surface that has maybe like, we use wax paper on a lot of surfaces because you can throw it out easily when it gets sticky. If that's just a little bit wrinkled, you can get resin on the bottom. And if you don't notice, which is very easy to not notice because you're not looking at the bottom of your tank, you put it in. If you then expose light to that area, it cures to the bottom. It's very annoying. And so we actually went and changed this tool to add more height to this because I was printing and I did this and I screwed up. Well, I didn't screw up an LPU, but I ended up with a situation that I had to clean up.
So we get the film, it's affixed to the bottom, the tension that's designed. Now tell me about these other components here. What are these, for example?
Yeah, so those are what we internally call wear strips. We have these in here because actually, I'm just kind of taking a quick shot here. When we actually put our mixer down, the mixer actually rides on this wear surface. So it's a nylon surface that goes back and forth. It is not directly contacting the film, and it's kind of a barrier between the mixer and the film.
The mixer and the release mechanism are sort of for different purposes. So the mixer has a number of things here, and it's sort of done different things in past printers. But here, it's mixing the resin, obviously, I suppose, but to allow it to heat up faster, make it more thermally uniform. So when we get to the LPU, we'll talk about the heaters that are in the LPU. But this whole area needs to be exposed so that the light can come up below it. So ideally, if you wanted to heat a big vat of resin, you would have a heater that is along the entire bottom, but we can't do that. So the heaters are along the edges. But if you just heat from the edges, there's a thin layer of resin. It won't move very quickly through the resin via conduction. So this mixes it. It both helps heat up time and temperature uniformity, which is important. And then it also does failure detection. So if a part comes off of supports, or that's generally like one of the failure modes. But if a part were to come off supports, the mixer will run into it, and this is driven by a stepper motor and an encoder. Actually, we didn't take off the front panel. We can get to that. And it looks for a deviation between the commanded position of the stepper and the read position of the encoder. And if it sees that deviation is too high, it will say, "I probably run into something, so let me stop."
Right.
And that's better than like continuing your print and wasting resin or causing your mess to be larger. So it's thermal uniformity, it's failure detection. And then we can also talk about the
what's
preprint.
So we have a preprint routine. If you are printing with our printers, you can kind of see our build platform come down in incremental steps, getting closer and closer to the print plane where our mixer is kind of swiping across, and at the point where it's actually physically contacting our build platform.
So I call it the wipe, right?
It's the wipe, yep. And at every stage, it's detecting if I hit anything that could be a tall part that someone forgot to remove. And then as you get closer, you're looking for any amount of debris that's left on from someone maybe chipping away a raft at a part. So this is actually a part that was really challenging to design into the mixer. It's a molded part that we ended up actually heat staking into the mixer body here. So this mixer body here is actually an extruded part that gets post-machined with all the right geometries and slots to not create bubbles and everything while we're wiping. And this gets heat staked in here. And this is almost like a compliant plastic spring that we're basically preloading onto our build platform. And as we wipe across, we use our force sensor to detect if there's a spike, which means we hit something, whether it's something on a part or maybe just overall debris that got reintroduced.
And that's really important, you say, for the preprint process. You don't make use of this mid-print, do you?
Yeah, just in preprint.
Yeah, just in preprint to basically stop it early if we're basically detecting that you're going to run into something or you're going to be printing on a part that's already
Yeah, obviously if you put a build platform with a part in, like a big part, that's a problem. But this catches like very, very subtle, small pieces of debris. You can print down to 25 microns, which is sort of hard to imagine how thin that is. So even just a chip of resin on the build platform, if that's there and say is like a few hundred microns, as you bring the build platform down for your first layer, you try to go to 100 microns. So you 100 microns of resin. If that chip of resin on your build platform is 400 microns, say, now your whole printer is actually like, you can't see it, but it's clamshelling open, and now you're exposing with enough energy to cure 100 micron layer, but in reality, there's, say, 500 microns of resin, and now you're not going to adhere to your build platform. And if you were to look at it, you might say, yeah, that's a tiny piece of resin. It's probably not an issue, but it can be an issue. And so this is catching macro scale problems, but also really small, subtle pieces of debris.
And this,
like that,
the mixer moves pretty quickly. Like your cycle time, you have to do, you have to expose, you have to lift, and you have to mix all in just a couple of seconds. And so that's pretty fast. Right?
Yeah, and all of those motions are coordinated. So if if your build platform's this big and you're printing something small and on the side, you don't want to wait for your mixer to go all the way across to go back down and keep going, because then all the period of time between when your mixer passes the part and when it gets to the other side is wasted. So the mixing routine is aware, and all the motion planning is aware of where the parts are on the build platform. We call it mixer dodging, so that we can really optimize every millisecond out of every aspect of the per layer routine. And then you were talking about speed of this thing, but it's also a function of material. So some of our materials are more viscous, which means they create more drag on the wiper. And so for the less viscous materials, we want to take advantage of the fact that the drag is lower. So we run this at speeds that if they had the more viscous materials, this would stall. So all of those speeds are tuned on a per material basis.
Right. We print a lot of Tough 2000, pretty viscous, and so it needs to
compared to a rigid 10K where there's a very high fill, and we kind of developed our mechanical systems around the most viscous resins. So we have overhead in our axis that we can look at later to know that we can always run faster on the least viscous resins and be able to do per material kind of wiper speeds.
Can you talk about this? This is something I haven't seen before in the tank.
Yeah, you guys are getting a sneak peek into something that we're going to start shipping soon. We talked briefly about the failure mode where debris is on the build platform, and in the first layer it touches the film, but the same problem can arise in the middle of a print. So if you accidentally leave a chip of resin in your tank, or if a very small part fails and it ends up in the tank, if your part comes down and squishes on that piece of resin, again, it will be trying to get to, say, 100 micron resin thickness, but it will actually be higher than that, and that can cause a print failure. It's very hard to see those in a big vat of resin, especially if they're small and especially if there are very few of them. So the idea behind these is that they sort of act as a sieve or a colander. And so as the wiper moves back and forth, it's moving the resin to one side, sort of flows over the top here, and then the resin drains out and any small pieces of material are caught in here. And so you can take it out, clean them out.
Actually, can we look at a build platform? I think it might be a good time to pull this up, because I have one here, and I know you guys brought a new one. So this is your standard build platform. It actually comes off of a printer that we've just used. So,
A little sticky.
Yeah, a little sticky. One question I've always had is how clean should this surface be? How free of gouges and scratches?
That's a good question. I mean, I guess there's like a few answers. Like when I look at this I would print on this. I'm not going to touch it because it's sticky. But like having a slick of resin like on there before you print is obviously fine. Some degree of like scrapes and gouges is fine. What you want to avoid is either pieces of the aluminum or chunks of resin that are like significantly proud of the surface because those will then contact the film on the first layer.
And with our BP scrape on our mixer, you would actually catch a lot of those, whether it's a significant gouge. But I think one of the like aluminum maybe disadvantages is that it gouges much easier, especially when you're using a stainless steel or a steel scraper. So in many ways, I think we've also designed a build platform flex that is a stainless steel surface. It's a lot harder to gouge and a lot more robust.
It's my least favorite part of doing any type of resin printing is that, and you guys have done a great job, having lips on the rafts to make it easy to pry parts off, and for the most part, parts pry off pretty easily, but having used a flexible build platform for the 4, that's been a life changer. So tell me about the development of that for 4L.
Yeah, so I guess this all kind of started from the design of the Form 3L build platform flex. We started thinking through a lot of different architectures for what is the best flexible build platform version that we can make integral to our printer. I think there's other options out there where you can attach a magnetic plate onto a standard build platform, but we really wanted an integrated system that we're able to release parts, use the build platform like we tend to in our wash systems. So we basically scaled the same architecture. So when you think about, if you see an F3L build platform, it has a very similar extrusion-based architecture. So it's actually pretty similar to a normal build platform here, but where all the kind of meat of the product is actually in this flexible sheet here that I'm going to take off here. So this is a separate plate that you print on. It's a stainless steel that's actually magnetic, and there's actually a lot of intricate welding here that we do with basically a laser welding line to constrain some of the rotation and motion when you're releasing.
And this magnetically attaches here when it's on and lets the pop off.
Yeah, Larry worked on some of the first iterations of this and is maybe underselling just how hard it is to get this to work reliably, because we've said maybe in the past, but there's really high forces pulling in this direction as you're printing. So the peel forces that the tank sees are also obviously seen at this build surface. And so you need to make sure that basically any geometry and any material printed anywhere on this will not result in the sheet separating, because as soon as the sheet separates, even if it comes back, if it's 50 microns out, you're going to see that in the print.
Yeah, so on the design side, basically we spent a lot of work getting the magnetic base. We kind of, essentially, we've used the mag chuck before. We want to make a mag chuck for this, but also make it so that it's releasable when you're actuating. So we have a really large Hallback array magnet under here that's basically kind of covered and hidden by this basically magnet cover here. And that's why when you put the sheet back on, back on, there's a nice little snap right over.
Sweet. We've mentioned the LPU and the BLU a lot, so I think we should get to a point where we can take those out.
That sounds good.
The panels are off, and you guys have this on a wonderful turntable. Can we do a turnaround, kind of take a look at all these components? Maybe just behind the front panel then. Okay, so what we removed, there's obviously a touchscreen, right? So you have a touchscreen. This is the ribbon cable for our display, power data, and what's all this underneath?
So that's we have a couple harnesses that we have run across the machine. This is our front harness that runs all the way across. It has a combination of things that break off into a speaker here. It runs across. We have our LCD cooling fans that run all the way to the back there, and also runs some of our cables up to the top here for our dispenses. So it's kind of a bundle of a couple of different sensors and fans. And then we also have another, if you rotate to the other side.
Is it routing from all the way around from the main board?
So we kind of split off in a couple different routes. So there's a lot of stuff obviously coming from our motherboard here. a majority of it runs along the front side and kind of breaks off into different pieces as it's going across, including the encoder board for the mixer. And we have another wire run for most of our power lines that goes through the back of the printer underneath our tower here. So you can see, well, this is a big old ferrite here that runs underneath and snakes back around. And this is our main power, it's kilowatt power supply.
Kilowatt power supply, how do you distribute, like what's distribution of power consumption across this machine?
The backlight is really the single largest power draw. Right. There's fortunately a lot of efficiency losses from the current that goes into the LEDs to the actual power that comes.
And you said 90% of that is just heat, just after it gets to
That's
the LCD.
90% just at the LCD. So 90% of the light that gets to the LCD, or I should say 10% gets through, 90% is absorbed by the LCD.
And then before that, you also have your lensing on top of your BLU. And
exactly. So there are some losses there, and then we don't necessarily capture every bit of light that comes out of every single LED. And then the LEDs themselves are on, I think on the order of like 30% efficient. So, for every, let's say 3 watts you put in, you only get 1 watt of optical power out roughly. So there's a bunch of losses there, and that's why we need a lot of cooling.
Yeah. And here, this is your drive for your mixer.
Yeah,
right?
so similar to our Form 4, we have a belt-driven system. I think we slightly sized the pulleys and belts for the forces and speeds that we run at for 4L. I think there's a kind of a tiny little screw in here, so it's important to get the right tension on the belt, and we have a little jack screw here. It's in assembly step where we loosen these slots a little bit, we tighten this screw, and we use a tension meter. Basically, if you just pluck at the right frequency, and then we tighten it down to get the right tension on the belt. We have an encoder disc here that's tied to our idler pulley. So as you are running across, it's basically tracking steps. And as Seth mentioned earlier, we're always looking at input versus output. And if we are trying to drive this and we're clearly not moving the mixer, we have stalled or hit something. And here is our really funky looking flag. That is our homing flag. This allows us to know exactly where the mixer is relative to the machine. So most of our moves, we have a homing routine where we do a coarse touch off, and then we come and do a slower, finer touch off. So we know, this is X equals 0.
This is the encoder right here?
Yeah, so this is our encoder right here. We have basically it's a encoder disc.
This is an optical system.
It's an optical system that's basically counting our rotation. So we calibrate at the factory, and we have both a homing and also basically a step count. Yeah.
So it knows based on how fast this is moving, how many of those black lines it needs to see, and when it might run into a little hiccup or stop. Yeah, amazing. There's also a camera, speaking of optical systems.
Yeah.
So over here, this is a camera. You guys introduced that in the Form 4. It takes pictures of a finished print, or you can do a time lapse. What considerations went into location, into operation of the camera module?
Location is a big one. I think we thought we architected a lot of the upper structure basically around knowing that we really kind of want this camera in this optimal position, which is looking at the entire print from all the way bottom to the top and getting an angle that's able to see that full field of view.
So there's a light here, and there's also a light here. These are independently controlled. I think we maybe alluded to this earlier, but these also need to be filtered so that they're cutting out the wavelengths of light that could also contribute to curing the resin, because you don't want to accidentally cure resin in the tank from these lights. And then you mentioned this, but for every single material, because they have different colors, they need different camera settings and also different lighting settings. So for every material, there's a different setting of power for front light and back light to sort of give the best quality images. It's one of the many steps in tuning like a bunch of different settings throughout the machine on a per material basis, both print process and otherwise.
Oh, one thing I wanted to ask about is this. This is how you measure how much resin is in your tank, is that right?
Yeah, so this is, we call it SANIC internally. It's an ultrasonic transducer. You can kind of see it from here, but it both emits a pulse, ultrasonic pulse, and then it measures the sort of the echo off of the resin. The idea here is that we want to measure the level of the resin in the tank and use that as a feedback loop with our dispense system that we talked about earlier. Then we get exactly the right amount of resin in the tank. And this is important for a number of different reasons. Obviously, the extreme cases, you don't want to overfill your tank, because if you do, you'll cause resin to slosh out of it. And if you underfill your tank, then you can potentially run out of resin, right? If you're either too much of an angle, you don't have enough resin. So we try to keep the resin height within a certain specific bound. But there's a bunch of challenges associated with making this work, but generally with making a system that can measure the level of different resins. And this has been sort of different across some of our
And it's the
past
different
products.
resins that make it tough because they bounce.
I think
With this sensor, this sort of gets around that problem, and it's not as much of a per resin issue. Some of our past sensors have had to be tuned on a per resin basis, which was pretty difficult. Actually, I guess going back to Form 2, that's the case, not as much on.
What's the accuracy of a kind of sensor?
Yeah, I think there's kind of two. There's like a still accuracy, which is I think on the order of plus or minus quarter millimeter. But when you think of our system, our resin is always moving when we're wiping. So when we're in action, it's probably closer to a millimeter or two. Luckily, we don't need resolution down to the quarter millimeter. But if you have a pretty standstill flat surface, it's a pretty accurate sensor.
I mean, a millimeter or two across that big of a tank is still many milliliters.
Yeah.
What is your safe operating volume in terms of your tank?
I guess we don't really think about it in terms of volume. We think about it in terms of millimeters of height, and assuming that you're within that amount of level. What is? I think it's
6 or 8 millimeters. I think somewhere around 6 or 8 millimeters for the set point. You can dump more resin in, but I think under that we tried to dispense. And at some point, as you're kind of wiping through, you do pick up some resin, so you just don't want to dry out.
So you guys call this the LPU, which is what you called previously the laser system, right?
Yeah. LPU stands for light processing unit here.
But this is a different system, obviously, and it's a LCD base. Can we flip this over? And I guess you want to talk about the top or the bottom first, because I know they're both interesting parts.
Maybe start with the LCD. I think like if you've used this sort of print in the past, you probably know what that means, but most people when they hear LCD, they either don't know what it means or they think about it as like the TV screen that they're looking at. We use an LCD here in a pretty non-traditional fashion, so you can't actually tell that it's an LCD, but this whole area with this sort of pebbly texture on the top, which we'll get to, is a liquid crystal display. Interestingly, this is actually off, but you can see visible light going through it because our display is optimized for 405, which means it's actually transparent in the visible spectrum, both on and off. But basically what this is a liquid crystal display. So there's a whole grid of pixels here, too small to see. They're 50 microns across. And every layer, we turn some pixels on and some pixels off, and the on pixels will be in the cross section of the part, which allows light through, and that cures your resin. So this is really like the core piece of the printer that is deciding what is and is not cured every layer.
Let's talk about the pebble texture. We saw this in the 4, but this is unique to your design.
Yeah, it's a subtle thing. If you were, just going through the printer, you might not even notice it, but this is really like one of the core pieces of technology that lets the Form 4 and the Form 4L both print really fast and print with less support. So those are generally directly traded off. If you have fewer supports, your part can accept lower forces. And if you have more supports, they're obviously more annoying to take off. And the faster you peel, the higher the forces are. So this is a long lead up to how this specific texture reduces print forces and reduces them pretty significantly, which lets us print faster and with fewer supports. So what this does is it allows, and it's very small, I mean, you can run our fingers over it and feel it. It lets air underneath the film as you're peeling up. So we talked earlier about how the part needs to separate from the film, but prior to that, the film needs to separate from this surface. If you cut a piece of that film out and you put it on a very, very flat glass surface and you tried to pull it up, it'd be like a suction cup. And so this lets air through. But the real challenge here is that it both needs to let air through and it needs to not screw up the light that is coming through, right? Or
the masking, right? Not just the light, but also the fidelity of...
Yeah, that's an even better way to put it, right? Is like if you have just a few pixels on a very small feature, if you move your film farther away or you put things in front of it that will refract the light, you will have your fine features affected in your print. And so the goal of this is sort of twofold. It's to allow airflow through, but it's to not change the direction of the light as it's passing through. So this is actually a micro lens array. And what's really difficult here is balancing those two things, is not changing the direction of the light, because changing the direction of the light will impact your part, but also letting airflow through. And so there's this balance of the height of the texture, the shape of the texture, and the effective lens of the texture. And maybe I think
I do see distortion, right? That's optical distortion.
But it's because your hand is far away. And this is a lens, right? So as you bring your hand closer, it comes into focus. And you can even, here you can see the lines on my hand. It's totally in focus, but out here it's not. And, that works in reverse.
Yeah.
Your print plane is right here. And so if there were no lens here, you could see your hand clearly at multiple distances. But here, the focal plane of this micro lens array is at the print plane. And so that is what allows us to print in like with crisp lines at the print plane. But you're right, if you move the tank an inch away, everything would be blurred out.
Right. And is it uniform distribution? Like, is my hand here, that's a uniform distribution of light passing through even between the bumps of this optical stack?
Yeah, that's correct.
Wow.
I think another interesting thing here, it's hard to show because the pixels are very small. I think people tend to read resolution and say like, oh, my printer has like 50 micron pixels, therefore that's the smallest feature that I can make. But there's actually a lot of nuance to it, and we can get to it when we talk about the backlight. But the light that is coming into this has a bunch of pretty important requirements. It both needs to be uniform, because if it's not, you'll have higher exposure over here, lower exposure here. You'll get different properties. Things will look different. But it also needs to be collimated. I think you don't typically like think about light in this way, but like a laser, for example, like you shine it and the spot size here versus the spot size way over here is very similar because all the rays are traveling together. They're not fanning out. That's actually really important here as well, because when the light passes through an open pixel, it has a distance to travel prior to getting to the resin. And so if you have very non-collimated light, you'll have light that comes through the pixel like this and light that comes through the pixel like this. And even if your pixel is very small, if your film is even just a little bit away from it, those rays will all diverge. And so like if you have a small pixel but very non-collimated light, you might have worse fine features than if you have a large pixel with very well collimated light. It's also a function of how far away your film is and a number of other things.
Photon bleed literally between the pixels.
Yeah.
Now, you're making light more collimated here at the BLU stage or at the LPU stage?
It's a good question. The collimation happens primarily at the BLU stage. So there's there's a trade-off between collimation and uniformity. In the extreme case, if your light were perfectly collimated, it'd be very hard to blend it to be uniform, and you'd basically be imaging your LEDs like pretty clearly across the surface, which would also be bad. So the lens array on the BLU, which we'll get to, is doing the primary collimation. This is basically, this texture lens array is basically, it's not collimating, but it's trying to just keep the rays all moving in the exact same direction.
All right. Now, two of the disconnects that we made, that's for the heater, right? And your heater is built into the frame here, is that right?
Yeah, that's this board that you're touching right here. And if you go around, you can see it's actually two boards, and they wrap all the way around because we want to get as much total area of heater in contact with the frame so that we can push as much, drive as many watts as possible from the heaters into the frame. And then we also, Larry mentioned this temperature sensor, which is directly measuring the bottom of the film, which is a very good proxy for the resin. We also have little temperature sensors here and here that are thermistors that we use to prevent the heaters themselves from getting too hot.
And this is a different way you guys are heating resin from like the Form 3.
Yeah.
Form 3, it was like a heated
system.
blower, you're heating the whole volume.
Yeah.
Tell me about the philosophy of, where it's important to have the resin heated. Is that more of a power efficiency? Is it more for print quality?
Yeah. I think air heating, we try to move away from that architecture mostly because it generates a lot of just VOCs. I think you're heating the resin, it recirculates. And I think we spent a lot of time trying to drive down the smelliness of printers, which is kind of interesting to think about. But this is kind of keeping it all contained within the LCD module, which is essentially a big old heat sink. It's nice in that it's just contact heating, and we don't have a lot of circulation of air that could have, like our monomers evaporating from our resins.
Yeah, so it is a little bit more efficient, but I think the monomers evaporating is really the key element here.
Do the resins change properties when they're heated? Like, if a resin's heated repeatedly, is that resin have a shorter shelf life, or is that different than a resin that's been sitting that you heat just the once?
Yeah, it's a good question. I don't think there's really any degradation in performance from heat cycling the resin. But resins do, the reason we heat is maybe worth talking about. There's a number of reasons. The primary one is that the printer is going to be used in different environments, and the reaction rate and the performance of the resin, as well as the viscosity, all vary as a function of temperature. And so if we didn't have heaters and you were printing in a cold room versus a hot room, your prints would perform differently. Your resins would be of different viscosity. Your reaction rate would be slightly different. The viscosity is like a really apparent one.
Yep.
If you run in a cold environment and you don't heat your resin, if we're driving the mixer at a high speed, if the resin is too cold, it'll be more viscous and it will skip steps, as opposed to once it's heated up, it won't.
Is there a wide range between optimal heat for different types of resins? Or are they all fundamentally around the same
It's not
temperature?
a super wide range, it's like 40 to
Yeah, I think anywhere from like 35 to 40.
Yeah,
I think our
35 to
hottest
45.
resins go to 45.
Got it.
Yeah, but it is like resin dependent. And I think like as Seth mentioned, like how fast we can heat directly affects how fast we can start printing. So if we can instantaneously preheat to that temperature,
Right.
that's where all the wattage matters from
Yeah.
coming out here. You're not turning on your BLU for the first 10 minutes of your print.
This is actually similar to fuse. Like if you look at the power draw over the course of a print, it's very, very high at the beginning as it heats up, and then it levels off significantly.
Yeah, and then just maintaining more consistent temperature and having that
Same
feedback.
as FDM printers for a heated build plate or something, right? Yeah.
Totally. I mean, most heated systems are sort of like this.
Yeah. And then the actual data goes over HDMI, right?
Yeah. We this was like an intentional choice because we knew that this was a connector that is something that people are familiar with, and also that can be like plugged in and disconnected frequently without risk of breaking. Like we could have run this connector directly to it. But this is something that people are less familiar with. This like
It's a finicky interface and EDP connection, basically.
yeah, so you can take it out, but like tiny little connectors. I'm gonna try to get it back in there.
How much of that is a consideration to the future life of this printer? And you guys have chosen a part an LCD with a specific pixel dimension, resolution. Is there a consideration that sometimes somewhere down the line, or if we might have a different component that might get swapped in here, that this just becomes an easy swap out?
Anything's possible. We've tried to make these different parts of the system easy to change, both so that like we said, they can be swapped for new versions if they break. We also do a lot of prototyping in house with like different various versions of this.
How much of a decision did you guys have to make, or could you make, about like the size and aspect ratio of this?
Yeah, it's a good question. These are actually both this and Form 4 are custom design screens. So it was totally custom. We wanted something that was rectangular as opposed to some of our past products that are closer to square, because they give you, we think generally like better overall usage of the build area. But yeah, these are custom screens. We really tried to optimize for transmission here. That's like a key, one of those key specs that maybe like a user never thinks about or never cares about, but it's actually really critical. We talked earlier about how like you lose 90% of the light that's passing through the screen. But that was a hard-fought 10% transmission, and if that were to be 5%, it sounds like a 5% difference, but it actually means that you lose twice as much, and that directly translates to print speed and to cost and complexity, because you have to add like more cooling. So getting the screen custom, saying like this is how many pixels we want, this is the size. That's sort of the easy part. The hard part is like trading off these other elements. I actually think this is maybe another interesting aspect. There's a pretty direct trade-off between pixel size and transmission. The reason for that is that here it just looks clear, but if you zoom in and you look under a microscope, every pixel is like a window, and there's a border around it.
Pixel fill, right?
Yeah.
Screen door effect. Yeah.
Exactly. And as the pixels get smaller, the borders don't get smaller with them. So your total ratio of open area to not open area gets worse. And so we made we thought a lot about the trade-off between total transmission and print speed and pixel size. And so we experimented with a lot of different pixel sizes. We ran a lot of different prints, things that we knew would look better or worse at different pixel sizes, and then sort of looked at the trade-off between the print speed that we bought with better transmission and the fine feature performance that we bought with better pixel size resolution. And we talked earlier about like collimation of light from the backlight, but that was another contributor there where maybe we wanted better fine feature resolution, but we really wanted the transmission of the larger pixel, so we could then improve the collimation of the light out of the backlight and get better fine features, even if we weren't actually just making the pixels smaller.
If the pixels are smaller, do you compensate that? Is it just increased power in the backlight? Do you have to add some kind of aliasing diffusion to make up for that negative space?
So that's a good question. The area between the pixels is black, and if you were imaging resin directly on top of that, yeah, you would have gaps. But in reality, like the print plane is far enough away and the light is not so perfectly collimated that we've never actually run into the issue where you don't have pixels meeting because of the gaps between them. So we don't ever have issues where pixels are like, the gaps between pixels are actually imaging onto parts.
I always talk about light a lot and that backlight unit a lot, so I think it's time to get that out of here.
Yeah.
The BLU, massive. Is most of this heat sink, right?
Yeah, I think most of the weight driven from here. Actually, you will be surprised if once we get the lens out. The lens is actually quite heavy because it's a solid, now basically acrylic lens that we're molding, but most of it is the heat sink. And we have 2 cooling fans under that does axial cooling to basically keep the entire backlight unit cool and uniformly cool across the entire LED array.
Yeah. So whereas the LPU had the uniform bumps for air for the release of the film, here it's all lensing for the collimation of the light.
Yeah. So these lenses do a couple of different things, and we'll get to the LED board. But first, they try to capture as much light coming out of the LEDs as possible, right? Because you can't capture all of it, but you want to get as much as possible. That sort of directly translates to more power at the print plane or less heat, less cooling. And then it also both collimates and it like makes the plane uniform or the field uniform. So it does both. Those are not, they're actually kind of at odds with each other. And so we try to strike a balance here of collimation and uniformity.
Yeah. Was there ever a world where the 4L was just going to be 2 4s kind of sandwiched side by side, kind of like the 3L and the 3 with 2 LPUs?
It's a good question. I think this is a little bit larger than that, so we wanted more size. But like Larry said, it's very hard to strictly sandwich things together and not get seam lines. Like really, the subtlest of things will image onto your parts. One thing I think is like generally interesting about a lot of these problems is that we don't go into them saying like, here's our clear spec, let's go design a system that has this spec. At the end of the day, the spec for all of these printers is that they produce excellent parts, they do that reliably. And so we have these very high level specs, speed, part quality, et cetera. But it's infrequent, it's not frequently obvious like how that translates to, say, a collimation spec or like an off-angle light spec. And so lots of what we do for things like this is we build them, then we test them and we print on them and we see what they do, because it's very hard to say like, you know, when we get below this value, it's going to be good, and we get above this value, it's going to be bad. And we learn more about that over time, but it's often very, very complex.
All right. So these are the LEDs.
These are the LEDs, yeah.
All 145 of them.
Yeah, 145 LEDs.
Tell me about the sourcing and finding the right LEDs to use in this.
Yeah, it's a big challenge. You both need the right power, you need the right reliability. These all have their own lenses on them, so you need to find an LED that has an optic that you can design around. So that is, there's two sets of lenses here. There's this lens where you're trying to capture as much of the light coming out of the die of the LED, and then there's this lens array where you're taking that, collimating it, making it uniform. Then we also try to get, our high level spec is we want to have this much power at the print plane, like so many milliwatts per centimeter square. And then that ends up informing what our selection of specific LEDs are here, right? You don't want like 3 super high power LEDs because they're going to be harder to collimate, make uniform. You also don't want like thousands of them for cost and reliability reasons.
Right.
But there's a pretty broad range of like number and power of LEDs that you can trade off in different ways. The other thing is that you ideally want exactly the same amount of power coming out of each and every one of these, but that's obviously never the case with anything. And so for every single one of these, we build them up, we fully assemble them, and then we measure the power output out of them. That varies within a range. That calibration value we store on this unit. So if this backlight that we're tearing down, has slightly more power output than that one that we pulled out of the printer, if you were to swap them, you'd end up getting different performance at the print plane. And so we actually store those calibrations on a per unit basis so that if you swap this one into the printer and took that one away, you'd still get the exact same power at the print plane. And we actually do the same thing on the LCD because it has, transmission varies slightly. And so you take those 2 values together and you can say, although they both perform differently, we can control this in such a way to get like the exact number that we want at the print plane.
Is there any reason, and I assume all these LEDs fire for every layer?
Yeah, that's currently.
Is there any reason to not have them fire for every layer?
Yeah, there's definitely reasons you would consider doing that. It's more efficient from a power perspective, which like from an electricity draw perspective, and really the driver, but from a cooling perspective is, we mentioned earlier that the LCD's lifetime is generally a function of total fluence. And so like not sending light through parts of the LCD that you're not using is ostensibly a good thing, but in general, these lifetimes are so high that we haven't found that that's like a meaningful factor. But it would generally just mean that you have less cooling requirements.
Okay, it's something that you could do dynamically just in firmware to, have the slicer make the system aware of which LEDs.
Yeah, that was sort of how you would architect a system like that. We thought about it.
No, during development, I think there's one critical like alignment spec, which is basically getting the lens centered on each LED. So both centered and XY, and also the Z spacing matters a lot, down to literally the like hundreds of microns.
Really?
So like if you kind of actually look closer here, we were contemplating a lot of different strategies and how do we want to center this lens array on the LED, and we ultimately ended up going with a system that depends on basically elastic averaging. So there's pins on all around the perimeter here that's basically preloaded as fluxtures to center the lens perimeter around the center of the LED board. And if you kind of pop them out, you can actually see as you're installing in, these are kind of little flexure pins.
Oh, yeah.
Yeah, so that's like definitely a strategy that we've like implemented early on, did a lot of validation on, actually by 3D printing a lot of these baffles to kind of validate that. And then for Z height control, it's really hard to hold injection molded plastic pieces down to really tight tolerances, definitely tight. So what we ended up doing is actually insert molding in precision machined spacers to get the height control. So when you tighten the entire lens stack down, your height between the LED and the actual lens is driven by an aluminum standoff across the entire board. So
and then it all gets tightened together.
It gets all basically preloaded together all the way down. And as I mentioned, I think flatness of the lens, definitely, this is pretty flat, but not perfectly flat. But the way we actually designed the mold and looking at mold flow is to make sure we are bowing kind of down in the middle. So when we tighten down, your center makes contact first and you're pulling down.
Got it.
If you're warping like a potato chip this way, if you're coming down, you're actually bowing the opposite direction. And then now all your lenses are at slightly different off angles compared to the LEDs across the entire print plane.
Yeah. Knowing how this is going to be assembled at this size.
Right.
Yeah, you go backwards and
Yeah,
make the offset in the manufacturing.
Definitely, and this is kind of interesting, like just kind of diving a little bit into molding. Like you got to inject plastic some way, and this is acrylic. So we actually inject with multiple large gates here. So this is where the plastic flows in, and you're kind of filling this part from the short side here to the short side there. And what we're actually doing to modify some of the like temperature gradient is you can basically do a time delay fill. So you can start off filling here slightly faster than you start to fill the middle two. And depending on kind of what that temperature front looks like, it actually changes the final like output of the part. So it's like one of those where it looks, this is a crazy part. This is like if you go into like, college, they tell you to design injection molded part. This is like this is a very standard molded part where everything's poured out. It's where this is like, at the thickest portion, 15 millimeters, at the thinnest portion, maybe 6 or 7 millimeters. So like variable throughout, but we need that for lens performance. And we worked with a optical injection molder that knows what they're doing to actually get this. And on the backside, we do also have actually a diffuser film layer that we end up laminating on here. We did also like think about, could we do this on the mold texture side?
Right.
We probably could have, but I think at that time, I think it was easier to put the film on and not kind of iterate through different mold textures.
So increase your yields potentially?
Yeah, and just give more flexibility
More
early
flexibility.
in the design process.
Okay.
But yeah, you need some, diffusion is sort of like contrary to collimation, which we've been talking about is super important, but if you have no diffusion at all, you can't see it. But the LEDs themselves have a size, they're not perfect circles, they're dies with rectangles, and you'll actually end up imaging the exact die onto the print plane, which you also don't want to do.
So you're diffusing just to have it even and then straight up so the photons are aligned through the baffle, through the lens, through the LPU onto LCD.
And all of these things, like really every single one of the things we talked about, like there's all sorts of additional details, but like every single one of these, if you get them wrong, they'll show up on the part. It's not always obvious like why, but we print extensively throughout the process because it's not always obvious like what this being not flat or, having weird moldful artifacts, like all of these things can affect printing, but it's not always clear. And so we try to every step, like we didn't first make this whole lens, we made a very small version of it. We printed on that, we tested it.
So going back up, you got the BLU, you got the LPU, there was the tank, your build platform, and then the build platform rests on the Z-axis, the Z stage.
Yeah.
And I know you guys brought a separate one because we didn't want to necessarily take apart one to ruin the calibration. Can we take a look at that Z stage?
Yeah, for sure.
Okay, the Z stage.
Yes. So I guess we've historically had single linear rail systems. I think going to Form for All, as we talked a little bit earlier, like stiffness is something we're thinking about a lot when we're designing the printer. And this is everything from LCD through to the entire system back into the build platform. So it's kind of making this clamshell or this C bracket. So the linear rails is actually just one component of 10 things that contribute to the entire stiffness stack. And we decided to implement a basically two dual linear rail system to get the Z stiffness so we can squish faster. We have a higher system stiffness, which translates back to print speed. Yeah.
Got it. Yeah, technically, yeah, because 2 rails here. Right. And of course, the build platform just latches in. One of the things I love. The 4 and 4L, there's nothing to tighten, right? It slides in.
It's a drawbar mechanism. Yeah, so actually we actually started off doing a top-down latching mechanism, similar to Form 4 and Form for All. What we actually ended up realizing is, to get the mechanical advantage to be able to draw this build platform, it drove a height of the latch, which actually ended up driving the printer height because you need hand clearance on top. We're like, that doesn't feel great to have a latch come up. Now you're also adding another 50, 60 millimeters of printer height just so you can get your hand on there. So then we started thinking, can we make a side drawing mechanism? So we actually have a latch that basically converts a translation left-right into a draw of the BP upwards toward the Z stage. So again, there's actually 4 screws here that we use for parallelism adjustment. And to be able to get this, what we call Z-truss assembly out, there's a little clever thing that you have to do is actually just push up on the drawbar here and you can take the latch out. So this is actually the latch that we'll see later basically cams this drawbar and pulls up against the build platform into these hard stops here that are located to the printer. So it's all hidden, but there's a lot of stuff, I guess, under the hood here.
And basically that amount of torque, that gives you presses against.
Exactly. So generates the preload. And that force is important because we want it properly preloaded because the build platform is constantly getting tugged at during peel when we're separating from the film. And if we ever break that preload, we're going to see it on the part, and we definitely don't like that.
This happened a couple of times really early in development. We'd get a part out, and it would have a lot of things that can cause a line in a part, which is frustrating because you get a part with a line out, and you're like, it could be any number of very different things. Right. But if you see, we would see parts where there was a line that wasn't like an XY shift, but was a rotation. And we think that what was happening was we didn't have enough preload in earlier versions of this, and some of these forces, although they shouldn't really translate to theta Z, would cause shifts in the BP. And if you printed part of your part and then there's even just a 50 micron, something very small shift,
very noticeable.
You'll see. Like the human eye is really, really good at picking up really subtle things, that, small things like that. Larry's been talking about parallelism setting, but the planes that are created by the LPU, which we were talking about earlier, and the build platform, those need to be as parallel as possible. And any degree that they are out of parallel means that when you are down at that first layer, you will either be too close or too far in one area. And if you're too close and you're out of parallel, you'll actually press into the LPU. And if you're too far, then you may not penetrate sufficiently into the resin and cause your part to adhere to the build platform. Yep. The challenge here is that these are really subtle differences. We're talking like 100 microns over pretty large areas. And this needs to work with different LPUs. So if your LPU breaks, you need to be able to put in a new one, and reset parallelism needs to work across build platforms, which is a primary driver of like the flatness and dimensional tolerances of the build platform. So this is actually new in this generation of printer. We weren't able to reset parallelism in the past. So it means both that we can get a tighter parallelism spec and that in early layers, if you know that your parallelism is worse, the way to solve for that is to expose early layers harder or at a higher exposure rate. And the downside is that those parts are then harder to remove from the BP. So in general, actually I think all parts on 4 and 4L are easier to remove. And the reason for that is because we have better parallelism in general between these two surfaces.
Yeah, and it's a tool that's both user user interactive from the form for our user, and also at the factory, we are also using this for calibration. So we build up the entire system. We put in the LPU that it's getting shipped with. We do a factory calibration with a factory calibration jig, and then to validate that we're actually setting it properly, we actually run our first print at the factory. We call it our first test print, F2. I think that's what FTP stands for.
I'm never sure if F is for factory or first.
Factory test print. I think that's right.
Factory,
and we are basically printing to double check that our build platform is printing evenly across the entire print plane. And if not, we will go back and basically reset parallelism and set it again.
I know, in your HQ, you guys have like a room full of like Form 4s that are running nonstop and for just validation and optimizing all the presets that you have. Does that information directly graph onto 4L, or does 4L need its own type of validation and testing?
It depends. In general, we do that for both. Things like this system is sufficiently different that it needs all of its own validation. But from a material tuning perspective, which is like where a lot of that effort goes, and I imagine the specific room you're thinking about where there's just like walls and walls of printers, that is not lifetime testing, that's materials tuning. So we'll we have a very a process that we have refined over a number of years, and a whole team dedicated to tuning settings. So there's like a million knobs in the printer that you can fine tune to make your print behave differently. And so we can take some of the Form 4 settings and say like the material is fundamentally the same thing. That gives us a good starting place, and we'll use that as a starting point for a 4L setting. But there are subtle differences because the hardware is different. Every one of these is a trade-off, right? Like there's there's engineering work and cost and risk that goes into making the LPU and the BLU replaceable. In the end, we decided, and I think they were the right decisions, that those were worth it. But things like this, for example, where like the perpendicularity of this stage with respect to the LPU is super important with respect to the rest of the frame. So like there's probably some world where we could have made this replaceable part, but like we decided that weighing all these things against each other, this didn't make sense. And so, like Larry said, we
lifetime tested to gain high confidence.
Make sure this is not a part that's going to fail.
Yeah. There's no single design element of a printer, this printer, any product, right, that does or does not make it reliable. But like in general, we're like pretty obsessive about reducing print failure rates. That is like a golden number to us. We track it really closely. We obsess over it. Me and a number of other people, we looked at every single print failure over the course of the last, let's say 12 to 18 months of the program. So that started out as a big fleet of printers internally that we were running, every single day, both engineers and a dedicated team of technicians. And every single print failure we would look at, we would debug, and that generated a lot of the work in the end of the program. Like in many ways, this product existed physically a year before we launched it. But we spent, really a year sort of like obsessing over these tiny details, looking at every print failure, all the force logs, and that did generate a ton of work, right? Like when you have a relatively mature product, a fourth generation product, those gains in print failure rate or print success rate, we think about failure rate because the number's a lot lower, and so small changes in it are actually really impactful, right? Like the difference, in a percentage point is a huge number of customer prints that are no longer, that are going from failure to success. And there are little details throughout the printer, the software, the settings, that you'll never see, and I can't even like stand here and list them all. Together, like as a sum total in conjunction with like all of these subtle design details, like that is what makes something that at the end of the day like just works. And that's generally what we aspire to do, is like focus on these details that really drive print failure rate down and make this something that is like a tool and that really never fails. And it's hard. Like I think we still have a lot of work to do, and we're still obsessing over any sort of print failures that we see. But maybe personally, not a single design thing that I'm most proud of, but like having looked at every single print failure, thousands and thousands of prints and hundreds of failures is like really was a lot of work.
And this is like a sentiment I think travels through like every level of product, like every level from the leaders of the programs down to every single engineer that's working on their systems. They're always thinking about how to make it a cost-efficient system, a reliable system, like what's going to fail, how can I design that out so we don't even have to worry about it as a risk. And I think this is really like a lot of tiny pieces coming all together for a product that I think is something we're all proud of, and it's definitely like no easy. I think designing product, everybody's like kind of thinking through like when I first started, it was like how easy is it to design a printer? We've done multiple printers in the past, and every time there are new challenges, different types of systems that are going to be the new challenge, or like overall, it's a big effort, and I think we have a good team that's driving that. Yeah.
Well, I appreciate all the effort, both on both your parts and your team's parts. It's one of the reasons we love
mostly our team.
Yeah, mostly that. But it's one of the reasons we love printing on this is because we get to have parts and we spend less time, fixing something or tuning something, and that's all done. That's all that consideration that you guys have put in.
Sure.
So the challenge for me, I guess, is now let's see if we can put this back together and get
together.
a print out of it. So yeah, let's rewind the tape, right?
Yeah, we'll just
run it in reverse.
Go back, and it'll be a perfect printer like the beginning.
All right.
I think we can do it.
Okay, that was pretty painless. Reassembly.
Yeah, it was pretty easy.
How many printers have you guys put together? The 4L.
Personally, I've
Lots of bits and pieces.
Yeah, I've probably done 5 to 10, maybe throughout different prototype phases.
Yeah, Larry more than me.
Yeah.
Probably put together more than anyone outside the factory, I would think.
One of the cool things as we're taking it apart and putting it together is clearly how much you guys care about all the details, from not only the functionality, but the aesthetics, where the countersunk screws are, to the radii of these corners here. But we feel confident. Should we turn this on? It's plugged in?
Let's give it a shot.
Okay.
Yeah.
All right. I love a moment of truth. So here we go. Eyes on the front. We connected the screen, right? Oh,
Yes,
there it goes.
It takes a little second.
Was that the Z-axis locking up?
Yeah.
And then I also will do a homing routine to bring it back to the right spot.
There we go.
It's booting up.
It's booting up. Maybe not at full speed. It's thinking through a little bit. Coming out of hibernation.
Hey, there it goes,
home.
initializing.
So there's the axis, x-axis is homing.
Oh, and it goes
Welcome.
welcome. I think we
Great.
did it, guys.
Nice.
Well, thank you guys so much. I'm going to peel off the protective film. May I have the honors?
Do it.
Awesome.
Please.
Fantastic. So satisfying. We're, of course, going to make sure this printer operates and runs and get some wonderful prints out of it. I want to thank you both so much for spending the time here at the studio, walking me through all these design decisions, everything that makes up a 4L. Hopefully it was fun for you guys too.
Yeah, it was a pleasure. It was
It's
awesome.
fun to talk through all these things, yeah.
Yeah, a little bit of therapy, right? After the product goes to market. Okay, awesome. Thank you, Seth.
Yeah, thanks a lot.
Thank you,
Norm.
Larry.
Thanks a lot, Norm. Thank you.
Thanks for watching. We'll see you guys next time. Bye.